Hello and welcome. Imagine you're at a concert where two speakers play the same tune, but sometimes the music sounds louder, and other times it seems to fade away. Ever wondered why that happens? Well, that's the magic of wave superposition. Here's a quick joke to get us started. Why did the wave break up with its partner? Because it couldn't handle the interference. Now, let's dive into the fascinating principle behind it. When two or more waves meet in the same space, their effects combine. This is called the principle of superposition. Think of it like adding two ripples on a pond. The new wave is just the sum of the original ripple's heights at every point. More technically, if we have two waves with displacements y1 equals a 1 times sine omega t, and y2 equals a 2 times sine of omega t plus a phase difference phi, the combined displacement y is simply y1 plus y2. So the waves add up. Whether the waves make the result bigger or smaller depends on their relative phase difference phi. If the waves align crest to crest, they boost each other for constructive interference. If a crest meets a trough, they cancel, producing destructive interference. This phase difference phi is the superstar controlling the amplitude. But there's a catch. To get clear and steady interference patterns, the sources must be coherent, that means they keep a constant phase difference. If not, the interference pattern becomes a chaotic blur. Coherence is the secret sauce for the beautiful fringes and patterns you see in many optical experiments. So the dance of waves is all about how they add up when they meet, and whether they play nicely in sync or not. Welcome back. Remember our joke about waves breaking up? Well, now we are witnessing the waves that stay together, coherent waves. These are the cool couples of the wave world. They have the same frequency and a constant phase difference, which means they keep their relationship steady and predictable. This allows for clear and stable interference patterns. Let's look at two coherent waves, each with the same amplitude, A, oscillating with angular frequency omega. The first wave is y1 equals a times sine omega t. The second wave lags or leads by a fixed phase difference phi, so it's y2 equals a times sine of omega t plus phi. When these two waves meet, their combined displacement y can be expressed as 2 times a multiplied by cosine of phi divided by 2, then multiplied by sine of omega t plus phi over 2. In words, y equals to a cosine phi over 2 sine omega t plus phi over 2. That means the resultant amplitude, which we'll call capital A, equals to a times cosine of phi divided by 2. So when phi is 0, cosine of 0 is 1, making the amplitude maximum twice the original. The intensity, which relates to amplitude squared, therefore becomes 4 a squared times cosine squared of phi over 2. What does this mean? When the phase difference phi is 0 or multiples of 2 pi, waves align perfectly and constructive interference produces bright maxima. Conversely, for certain phi values, destructive interference leads to minima where intensity is very low or 0. Picture the diagram, coherent waveforms plotted against time, perfectly synchronized, showing how they combine to form a stable resultant wave with fluctuating amplitude depending on phi. This explains why lasers, which produce coherent light, create those sharp, bright interference patterns we use in holography and other optical technologies. It's coherence, combined with fixed phase difference, that lets these interference effects come alive. Now, let's switch gears to when waves aren't the ideal steady couples, they're incoherent, like friends who can't keep a schedule. In incoherent addition, the waves come from sources whose phase difference phi varies randomly or rapidly over time. So, these waves don't have that steady tango but more like a chaotic dance party. Because of this, the interference fluctuates and doesn't produce stable patterns. Mathematically, since phi is random, the average total intensity becomes the sum of the average intensities of each source individually. In formula terms, the average intensity of the total wave is simply the average of A1 squared plus the average of A2 squared. No cross terms appear here because random phases average out the interference. What does this mean in real life? No fixed constructive or destructive interference appears. Instead, the observer just sees the total brightness as the sum of individual intensities. It's like turning on two separate lamps in the room, not a ripple of interference, just more light adding up. Common examples include everyday light sources like electric lamps or sunlight. They produce waves with short temporal coherence time, emitting many wave packets with changing phase relations, so no steady pattern emerges. Visualize the diagram showing multiple waves oscillating with varying phases, looking like jittery, unsynchronized waveforms over time, with no well-defined resultant pattern. So incoherent sources simply add brightness rather than creating the fascinating fringes that coherent sources give us. Let's get mathematical, but don't worry, we'll keep it friendly. Suppose two coherent waves have amplitudes of 1 and a 2, described by y1 equals a 1 times sine omega t, and y2 equals a 2 times sine omega t plus phi. When we add these, the total displacement y equals y1 plus y2. Now, using a handy trigonometric identity, the formula for the sum of sines, we can combine these into a single sine wave with an amplitude given by the square root of a 1 squared plus a 2 squared plus 2 times a 1 times a 2 times cosine phi. In clear words, capital A equals the square root of open bracket a 1 squared plus a 2 squared plus 2 times a 1 times a 2 times cosine phi close bracket. This amplitude tells us the height of the resultant wave at any instant. Now, since the intensity I is proportional to the square of the amplitude, it becomes open bracket a 1 squared plus a 2 squared plus 2 times a 1 times a 2 times cosine phi close bracket. So I equals capital A squared equals a 1 squared plus a 2 squared plus 2 a 1 a 2 cos phi. Why is this important? It quantifies how intensity varies with phase difference phi. When phi is 0, cosine phi is 1, giving maximum intensity of open bracket a 1 plus a 2 close bracket squared. When phi is pi, cosine phi is minus 1, producing minimum intensity of open bracket a 1 minus a 2 close bracket squared. This explains experimental observations of bright and dark fringes in coherent light experiments. Patterns arise due to varying phase and resulting intensity oscillations. In the diagram, a phasor vector representation beautifully shows two vectors a 1 and a 2 separated by an angle phi, adding tip to tail to form resultant A, where the angle phi controls their vector sum. Understanding this vector addition helps us see interference not just as waves in space but as vectors adding up, controlling light's brightness and darkness. What does it take to get those beautiful interference fringes? Let's uncover the conditions that make interference possible. First, the sources must emit waves of the same frequency and almost the same amplitude. If frequencies differ too much, the interference pattern will wash out. Amplitude equality helps get clear visibility of interference. Next, the phase difference between their wavefronts must remain constant or very slowly over time. This relates directly to coherence. Without that steady phase relationship, the pattern just disappears. Another key factor is path difference, represented as delta x, the difference in distances the waves travel before arriving at a point. When path difference equals n times lambda, the wavelength, where n is an integer, we get constructive interference, bright fringes light up. When path difference equals open bracket n plus 1/2 close bracket times lambda, destructive interference occurs, dark fringes form. If the sources are incoherent and phase differences fluctuate rapidly, fringe visibility drops to 0, meaning no patterns, just uniform brightness. In the diagram, imagine the classic double slit setup, two narrow slits receiving coherent light from a source. The distance difference between paths toward any point on the screen determines whether the waves interfere constructively or destructively, resulting in the famous bright and dark bands on the screen. These conditions are the foundation of many optical instruments and phenomena, like measuring tiny distances, analyzing spectra, and even in fiber optics technology. Let's wrap up what we've learned today. The resultant displacement when two sinusoidal waves act coherently can be written as y equals to a times cosine of phi over 2 times sine of omega t plus phi over 2. This formula tells us how phase difference controls the resultant wave's shape. The amplitude A of two waves with amplitudes a 1 and a 2 and phase difference phi equals the square root of open bracket a 1 squared plus a 2 squared plus to a 1 a 2 cosine phi close bracket. The intensity, which you see in brightness, equals a squared. Constructive interference occurs when phi equals 0 or multiples of 2 pi, producing maximum intensity and bright fringes. Incoherent sources, on the other hand, lack constant phase difference, so total intensity is simply the sum of the individual intensities without any interference pattern. The key takeaway is that coherence, keeping phase difference constant and frequencies the same, is essential for observing interference. Without it, waves just add their intensities and the fascinating pattern disappears. So, wave addition is more than just math, it's about understanding how nature's rhythms combine or clash, coloring our world with dazzling patterns or plain brightness. That's it for today's wave optics adventure. Remember, physics is not just about equations, it's the story of how the universe's tiniest vibrations add up to paint the big picture. Keep questioning and keep chuckling as you learn. See you in the next session.